When examining ancient megalithic structures, whether the massive stones of Stonehenge, the immense platforms of Baalbek, or the perfectly interlocking walls of Sacsayhuamán, we inevitably confront one profound mystery. How exactly did early peoples move and position stones weighing dozens or even hundreds of tons? Even more perplexing are certain ubiquitous, unexplained features found across many ancient sites worldwide. Prominent knobs protruding from enormous stone blocks, peculiar holes drilled meticulously into stone surfaces, and evidence of repeated, controlled fires at construction and transport sites. Scholars have struggled to explain these practical, clearly deliberate features, often dismissing them as decorative or ritualistic. But what if these knobs, plug holes, and fire residues were actually part of an elegantly simple and deeply practical technological system? One overlooked for centuries precisely because it was hidden in plain sight. The key insight occurred naturally enough, around a simple campfire. Watching closely as leaves burned in the fire and observing others above the flames rising rapidly upward, carried by powerful thermal updrafts, one realizes something fundamental about heat and air. Fire creates buoyancy, a real and measurable upward force. Hot air rises with surprising strength, enough to lift small objects and visibly shake the surrounding foliage. Could the ancients have recognized and intentionally harnessed this very same principle? Tonight we'll explore a radically practical solution to the ancient mystery of moving immense stones, one anchored firmly in observable science, common sense ingenuity, and hidden in the enigmatic features of megalithic stones themselves. By reconsidering knobs and holes not as decorative mysteries but as vital anchor points and structural interfaces, we'll see how our ancient predecessors may have developed balloon-like devices, primitive aerostats heated by controlled fires, to reduce stone weight and dramatically simplify their transport. The evidence, when viewed through this lens, becomes surprisingly clear, practical, and compelling. The moment we shift from the question of what if to how, the entire theory moves from speculation into mechanical plausibility. Once the basic scientific realization is made that rising hot air exerts a continuous vertical lifting force, it becomes inevitable to ask what materials and structures would be required to make this force usable. That transition, from observation to application, is where the technological triad comes into focus: heat, lift container, and fixed point. These are not abstract concepts but real, interdependent physical components, and remarkably, each one is reflected directly in the archaeological record. The first is heat, the fire itself. At numerous megalithic sites, from the Nazca Plains to Avebury to various points along the Stonehenge-Sarsen route, there are persistent signs of controlled, repeated burning. Ash deposits, fire pits, and blackened soil often appear in conjunction with transportation paths or at base platforms of large stones. This is not evidence of random campfires or ceremonial burning. These are repeatable, fixed locations where heat was applied directly in the vicinity of heavy stone movement. The implication is clear. These were thermal staging areas used to generate the rising air necessary for lift. But heat alone is useless without a container to trap and convert that lift into usable buoyancy. This is where the second component, the lift container, enters. While no full balloon remains have ever been found, unsurprising given the perishability of skins and early textiles, the technological prerequisites were fully present. Animal hides were available in all early agrarian societies, as were strong plant fibers and vines for stitching and tying. In Egypt, fine linen was already in use during the Old Kingdom, and evidence of pitch and resin treatment points toward an understanding of waterproofing and thermal resistance. In the Andes, the Incas' rope suspension bridges attest to a mastery of fiber strength and engineering. It is fully within the capabilities of these cultures to construct a sealed envelope large enough to contain hot air for a short functional window, long enough to offset 20 to 40% of a massive stone's weight, turning an unmovable object into one that could be shifted or slid. The third and final element is the fixed structural point, a place to anchor and control the entire system. This is where the long overlooked features of megalithic architecture suddenly become central. Knobs and protrusions, sometimes called bosses, appear on stones at Giza, Baalbek, Sacsayhuamán, Easter Island, and across megalithic Europe. These features are not randomly distributed, nor are they decorative. They tend to appear at balance points, corners, or load-bearing edges. They are precisely where a rope would be looped if one were suspending a net, stabilizing a rising structure, or distributing tension to prevent lateral rotation. In many cases, these knobs were chiseled off after the stone was placed, further indicating they served a temporary construction purpose. Similarly, plug holes, cylindrical recesses cut into stone faces or surfaces, are almost always found in positions consistent with beam insertion or tie-down use. In Baalbek, plug holes are visible on the top faces of the trilithon stones, even though those surfaces are no longer accessible. In other sites, such as Göbekli Tepe and the megalithic temples of Malta, socket-like depressions are regularly found adjacent to heavy stones, despite no current architectural necessity for them. Then there are the flat surfaces, carefully prepared platforms and faces where stones rest or appear to have been temporarily staged. These surfaces are often burned, smoothed, or even polished, indicating a deliberate interface zone. Such areas would be critical for managing heat transfer during the inflation process, or for allowing friction-reduced sliding of a stone whose weight has been partially neutralized by lift. Taken together, these three components form the irreducible mechanical triad: heat, container, and anchor. They are not only plausible in isolation, they are found together again and again in the archaeological record, and when interpreted as interlocking elements of a single coherent system, they reveal what may be one of the most extraordinary technological adaptations of the ancient world. A lifting method not based on brute force, but on the clever harnessing of nature's own upward current. So, how might this have actually worked? Let's not begin with theory or speculation or symbols. Let's begin with the physical, the visible, the immediate. Let us step into a scene, not as distant observers, but as if we were there, standing at the edge of a prehistoric clearing, watching an operation unfold. There, in the haze of morning mist and wood smoke, a team of elephants strains forward, ropes stretched tight against their massive shoulders. But what they are pulling is no ordinary stone. It appears at first glance to be a creature, an enormous, bulbous, smoking dragon slowly crawling across the earth. Its flanks are rounded and heaving, smoke curls upward from its back. Beneath it, barely visible, is a flat megalithic block sliding across a bed of rolling logs. And here the illusion begins to fall away. The dragon is no beast, but a rig, a great stone slung beneath a swollen, leather-skinned balloon, its surface darkened and trembling with heat. The smoke rises from a fire tended just below the envelope, fierce, but carefully maintained. Several workers crouch beside it, stoking the flames, adjusting the position of stones and ash to manage the heat flow upward. The air inside the balloon expands and lifts, straining against the ropes that anchor it to the stone. The ropes themselves are thick, twisted cords made of fiber, plant-based yet tightly woven, looped securely around protrusions along the stone's upper face. These protrusions, the knobs, are not incidental. They are functional, placed precisely to distribute the tension evenly, to hold the net in place, to stabilize the lifting force and prevent the balloon from listing or spinning in wind. Their placement, and occasional removal after use, is evident in countless megalithic sites from Peru to Egypt. They were never decorative. They were essential. Along the stone's edges and tops, small boreholes, plug holes, except narrow beams, serving as supports and tie points for a tensioning frame. This frame holds the balloon envelope in a stable position above the fire, and the stone itself. It's a floating cradle, guided by ballast and corrected constantly by the team below. Men walk beside the rig, watching the ropes, managing the balance. Some carry long poles to nudge the balloon when it drifts off-center. Others sprinkle water near the base of the fire to prevent the envelope from scorching. Despite the immense size of the stone, the system moves, slowly, deliberately but undeniably, forward. The fire doesn't lift the entire weight. It reduces it, enough to turn a 20-ton block into something that can be guided with animal power across flat terrain. Ahead of the rig, a line of workers lays smooth logs. As soon as the stone passes, the logs are collected from behind and placed again in front. An ancient conveyor system, endlessly cycling. This is not ritual. It is not theatre. It is labor, precise, collaborative, intelligent. And every element in the scene, from the knobs and plug holes to the fire and floating envelope, finds its counterpart in the archaeological record. What once seemed mysterious or symbolic now resolves into something far more elegant. A technology built entirely from natural materials, observational insight, and the steady refinement of practice across generations. The smoke rises not from myth but from method. The dragon is real, but it is mechanical, not magical. And once seen this way, the hidden technology of the ancient world begins to come into view. By the time Egypt had reached the height of its monumental age, the principles that began with smoke rising from a campfire had evolved into a mature, systematized technology. The fundamentals remained the same: buoyancy from heat, lift containers of sealed fabric, control through ropes and rigging, but each had been refined. The materials were stronger, the scale was larger, the coordination more precise. This was no longer experimental work. It was industrial in its organization, though organic in its tools. The linen used in the Old Kingdom was no ordinary cloth. It was woven finely enough to wrap royal mummies in dozens of individual layers, and strong enough to serve as sails on Nile ships. When treated with resins, oils, or pitch, materials already used in shipbuilding and embalming, the fabric became more heat-resistant and less permeable, perfect for holding hot air. Thicker ropes, braided from flax or palm fiber, could bear the increasing strain required to restrain much larger balloons. And where open fires were once set directly beneath the balloon envelope, here we begin to see the use of distributed heat. Multiple fires, perhaps set at the corners of a platform, could channel hot air through simple flue structures, delivering heat to the central balloon without flame contact, vastly reducing the risk of burning the envelope itself. A rudimentary form of heat plumbing. With these advances, the scale of movement changed. The transport of immense stones from Aswan to Giza no longer depended solely on brute force or river travel. Stones could be loaded onto barges with partial lift assist at the quarry, moved along the Nile, and offloaded again using heat-assisted systems on land. The flat desert plains surrounding Giza were ideal for this purpose: dry, open, stable. Here, great blocks could be floated forward on reduced friction sleds, buoyed slightly by massive cloth-covered envelopes, tethered at 4 or more points with ropes anchored to carved knobs and plug holes on the stone itself. Fire teams managed the lift. Pulling teams, men, oxen, perhaps elephants, provided directional force, and guiding teams controlled the rigging, ensuring no lateral drift. But transport was only one phase of the process. What made this era extraordinary was the attempt to push stone vertically, to reach heights that had never been attempted before. This is where the two great projects of ancient Egypt diverged in challenge: the raising of obelisks and the construction of pyramids. For the obelisk, the challenge was stabilization. A single, massive stone, carved to a fine taper, fragile in its own way, had to be tilted from horizontal to vertical without cracking and set precisely into a prepared socket. The balloon rig here was not used to lift the stone high into the air, but to neutralize just enough weight to allow the structure to pivot. Several large balloons were arranged along its length, their combined lift calibrated to hold the stone just shy of its full mass. Workers used levers and ropes to begin the raising. As the stone tilted, tension on the ropes increased, and the balloons did the rest, counterbalancing, slowing the movement, preventing a catastrophic fall. The plug holes visible atop unfinished obelisks and the knobs left on many of them are not mysteries. They are control points, necessary to keep tension distributed as the center of gravity shifted during the raise. For the pyramid, the problem was different. It was not about raising a single monolith, but rather lifting hundreds of thousands of heavy blocks upward over a long period. Ramps help, but their incline cannot be too steep or they become useless. With lift assist, however, the incline can be sharper. Balloons above the lifting zone could support part of the stone's weight, while ropes pulled it upward. Fires, perhaps situated at fixed positions near the work ramps, could heat air fed into long linen ducts or flexible chimney tubes, sending a consistent flow into the envelope above. The stone would not rise like a bird, but its effective weight would drop, perhaps by a third. That is the difference between dragging and guiding. As construction rose higher, so did the balloons. Nets tethered to the rising stonework could anchor the lift structures to fixed points on the growing pyramid itself. Each course of blocks became a platform from which the next lift could be organized. A modular, rising scaffold, not built of wood, but of heat, cloth, and air. When Herodotus claimed that machines lifted stones from one course to the next, perhaps he meant exactly this. Not gears or cranes, but cleverly organized floating rigs, handed upward by coordinated teams. In both cases, whether stabilizing an obelisk or lifting pyramid stones, these systems reflect the same elegant principle: partial weight reduction through heat-driven buoyancy, managed through material mastery and mechanical foresight. What began as a smoky realization near a campfire had now become one of the greatest engineering achievements of the ancient world. Of course, not every structure fits neatly within the bounds of the Egyptian model. The theory of heat-assisted buoyant lift, though capable of explaining a remarkable range of ancient constructions, reaches a limit when confronted with certain monuments whose scale or precision surpasses even the most ambitious projects of the Old Kingdom. It is at this boundary that the theory does not fail, but evolves. Nowhere is this more apparent than at Baalbek in present-day Lebanon, where some of the largest stones ever shaped by human hands lie not only carved and prepared, but precisely placed atop constructed foundations. The trilithon blocks, each weighing upwards of 800 to 1,200 tons, are seated high on a platform with such accuracy that the idea of lifting them using even an advanced form of the Egyptian system strains belief. The knobs and plug holes are there, yes, and the surfaces are flat, but the sheer weight of these blocks places them outside the lifting range of any fire-based system known or theorized. This gap forces a new possibility into view, that this system of buoyancy-based stone transport did not begin in Egypt or even in the Neolithic era, but far earlier and at a far more advanced technological stage. At the edge of China's western frontier, deep in the Qaidam Basin, sits a site known as Mount Baigong. Scattered across the area are pipe-like structures embedded in stone and running deep into a nearby dried lakebed. While conventional archaeology offers limited interpretations, some chemical analyses have suggested the presence of ferric oxides and silica residues consistent with ancient hydrothermal activity, conditions capable of producing natural hydrogen gas. If the more controversial dating of this site holds any truth, it could place its use not thousands but hundreds of thousands of years ago, perhaps as far back as 200,000 years. It is in this context that we must ask the unthinkable. What if a culture, not lost but simply erased by time, had already mastered the principles of buoyant lift at a level more refined than fire and hide? What if rather than heating air, they captured naturally generated hydrogen gas, far lighter, more buoyant, and available in select geological settings? Hydrogen offers more than mere lift. It lifts with force. 1 cubic meter of hydrogen can raise more than 1 kilogram of mass, almost 10% more than heated air, and it requires no sustained fire to maintain. But hydrogen is volatile. It requires containers that are both light and airtight. And here, another ancient element appears, one so advanced we rarely associate it with the deep past: silk. Silkworms are native to China and, crucially, if they exist now, they existed then. Silk is not only incredibly light, it is remarkably strong with a tensile strength exceeding that of steel by weight. It can be woven into a dense, nearly airtight fabric. When sealed with resin or oils, materials also present in ancient Chinese practices, silk could plausibly serve as a hydrogen envelope. A balloon woven from silk, filled with naturally emerging hydrogen from beneath the earth and guided with expertly braided ropes, could lift masses far beyond the capabilities of fire-based systems. Now picture it, not the desert of Egypt, but the mountains of Lebanon, where colossal stones rest impossibly atop platforms. A crane would struggle, modern machinery would labor, but a balloon filled with hydrogen, tethered to a trilithon block, stabilized by silk-wrapped cords, guided by operators who understood both the physics and the risk, could, in theory, apply lift measured not in fractions but in full tons. And if that were so, if this technology truly existed, then Baalbek becomes not a mystery, but a monument to an era far more ancient than we allow ourselves to consider. The knobs and plug holes, control points, the perfect fit of the stones. A requirement when you're placing a multi-hundred-ton object with only one chance to set it right. The absence of records, time itself, the long erosion of memory, of evidence of continuity. This final case isn't a contradiction to the earlier model, it is its future, or perhaps its origin. A vision of what the technology could become, or once was. And if even a fraction of this is true, then the ancient world did not simply lift stones. It lifted the limits of what we believed was possible.